Welcome everyone. In this video we are going to derive a formula for finding the electric potential energy of a particle. So let's draw a particle system first. Perhaps we have a Q1 charge here and a Q2 charge here. Now there will be a force of attraction between these two particles. And that force of attraction, or repulsion actually, not necessarily attraction, that force is given by Coulomb's law. So it is called Coulomb Force, or electrostatic attraction, electrostatic force. And it is going to be equal to a constant, Coulomb's constant, times Q1 times Q2, divided by the distance between them, not the distance, the square of it actually. So this distance would be r. However, this is just a magnitude. This is not a vector. So how can we make this a vector? By putting a unit vector, like this. And we define r hat in such a manner. And it might be confusing. You might be saying, do we have a negative sign here? For gravity, we had negative. Well, we won't have a negative, and think of it like this. If Q1 and Q2 are both positively charged or negatively charged, if they have the same sign, same charge, then they're going to be repelling each other. So Q2 will have a force like this, and Q1 will have a force like this. And as you can see, for Q2, it is in the direction of r hat. And by the way, let me erase these. This is r hat, okay? So the way we define electric potential energy is as follows. We denote it with U, and we are interested in finding it at a point R. Well, we are saying we will base our calculations on a reference point and on the value of the electric potential energy on that reference point. So we have another U, we subtract it, okay? And we're gonna say this is R naught. Here, R naught is, as I said, it is important, by the way, to understand this. This is a reference point. This is the point where we base our calculations, a reference point. This is going to be equal to, by definition, the negative integral of, I will give you the integrand, but let me give the boundaries first, from R naught to R, so from the reference point to the point of interest, we will have the dot product F dotted with dr, where dr is an infinitesimally small distance. And we have a dot product here. This isn't a regular product, this is a dot product. And how do we take a dot product? I have a video about it. You can find it from the cards right now, and it is also in the descriptions part. Just as a side note though, basically you multiply the magnitudes of the vectors and then multiply that with the cosine of the angle between the vectors. But still, do watch that video if you don't know it. It is important that you understand where it comes from. So this is great. And now let's continue. We will have again the negative sign and then R naught, R. And by the way, notice that this is what we're trying to find. We are trying to find the electric potential energy at a point R. Okay, so never forget what we're trying to do. What do we have for F, the force of electrostatic attraction? It will be K, Coulomb's constant, Q1, Q2 divided by r squared, the distance between them, times r hat, the unit vector. This is, as I said, F. Then we have a dot product, and then we have dr. Well, dr will, it might have lots of components, but I'm just going to have two. I will have a radial component, dr r hat, plus I will have a tangential component. It will be d phi hat, okay? D phi hat. And notice that, even if we had other directions, you could say x, y, z in Cartesian coordinate system, those directions will be perpendicular to each other. And since we have a dot product in between, there will be a cosine of 90 degrees factor, which is 0. So every direction gets cancelled. Only r hat and r hat survives. Okay? Don't, please notice this. So since also tangential and radial directions are perpendicular, this also goes to 0. This cancels, and r hat times r hat will give you 1 because their magnitude is 1. As a result, we get a scalar under the integral, and this is what we want because dot product is meant to give a scalar. We multiply two vectors in a dot product to get a scalar. So we are doing fine. And what do we have then? We have the negative integral r naught r k q1 q2 divided by r squared, and then we have dr. Here we can take constants out of the integral sign. What are constant? Well, of course, Coulomb's constant k is a constant. We take k out and let's have negative k. Also q1 and q2 are other constants. We also take them out. q1, q2, and then we have an integral sign again. r naught r. Here you notice that we have r squared in the denominator. So if I want to express it in the numerator, I need to say it is r raised to the power of negative 2. Of course, we have dr as well. And we will continue on the new page. So we have from the last step k, negative k, q1, q2. Well, what is the integral r negative raised to the power of negative 2 dr? We are going to increase the power by 1. So we will have r raised to the power of negative 1. And then we will divide by the new power. So we have negative 1. And if you don't believe me, just take the derivative of this thing. And you will see that you will get the integrand. That is r raised to the power of negative 2. But of course, we also have our boundaries. And the boundaries will be, I actually want to erase this. I don't like the dashed line. So we have this, as I argued. And we have the boundaries r and then an r naught. Great. We see that these negatives become positives. Okay. And we can take this r raised to the power of negative 1 back to denominator. And if we do that, we get k, q1, q2 divided by r. We have the boundaries r and r naught. So if we substitute our boundaries, what do we get? We will get, let's do it with blue, k, q1, q2 divided by r. And you don't even need to put vectors, arrows anymore, because after this step, we don't have a vector anymore, we have a scalar, so you don't even need the arrows, okay? But if you want, you can keep it. We substitute, don't divide by a vector though, okay? Don't write it like this. We need to divide by the magnitude of the vector. Then we have the minus sign, and we have k, q1, q2 divided by r naught. Here, we will now choose our reference point. We will say, and this is the convention of doing this, we will say, hey, look, if I look at this force formula, I see that when one of the particles is very far away from the other one, the force between them decreases. The force between them will be very small. So it makes sense that when the distance goes to infinity, there is no influence. Okay, when one of the particles is far away from the other, there is no influence on that particle by the other, and vice versa. So I say I want to choose r naught as infinity. Okay, it is, well, let's do it like this. It is going to infinity. And as a result, r naught will, logically be 0, because as I said, we can even see from the force formula that the effect of the particles decreases. It becomes very close to 0 when we have huge distances, and if we take it to the limit, then the u at our reference point of infinity becomes 0. So if we substitute this, and remember, this is equal to UR minus UR naught, right? Let me separate this. We had said it at the beginning. It was here. It came from the definition. We said this, and we just set this U of R naught to 0, and we substituted infinity for this. Well, if we divide by a huge number, what do we get? We get a very tiny number. So we basically get 0 in the limit. This goes to 0. And look at this. Look at this. We now have a formula for the potential, the electric potential energy at a point R. It is going to be, and you can put the vector for the argument. It doesn't really matter. This is going to be K. This is just this guy. K times Q1 times Q2 divided by R. And this is the formula that you can use while analyzing the electric potential of a electric potential energy, excuse me. There are different things. This is the formula that you can use while analyzing the electric potential energy of point-like particles. So I hope this video was helpful. If you have any questions, please drop them in the comment section. I hope to see you in another video. Until then, take care.